Okay. So, what we have started exploring is the frequency output of the oscillator we are targeting, which is we have proven that that should be omega c into kf into mt. We have defined what is omega c and what is kf. Okay. So, this is something we have already discussed, right. Now, FM generation, once we have this circuit, that means a particular oscillator with an inductor which is fixed and a varicap where it varies with the input that bias voltage. Okay. So, once we have that, we will be getting the output oscillation frequency is accordingly varying. Okay. So, what I will do, if you now start giving a input voltage as your MT into that varicap, immediately the output oscillation that you will be getting, that must be FM modulated signal, because that will be the MT, immediately the oscillation frequency, suppose it generates a cos some frequency. So, that must be this. Okay. So, and immediately you will get if this is the frequency, the phase will be omega ct. This is something we have already explored, that should be kf integration minus infinity to t m alpha d alpha, that is actually the FM modulated signal. So, that gives me a direct modulation where this kf is something which is chosen by that particular varicap, right. So, whatever I choose as my VCO, I will be getting accordingly the FM deviation and everything. So, I can choose my parameter accordingly and I will get my FM. So, I have to choose accordingly the free running frequency for that FM as well as the kf value, and that will give me the correct output, right. That is called the direct method. So, you can see already lot of complicacy that were arising from narrowband FM and then with the indirect method to generate wideband FM, that goes away. And of course, there was a problem that narrowband FM, it is not, if it is not sufficiently narrower, then there will be a tan inverse of kf into AT term, right. So, instead of just kf into AT term. So, that problem was there, whereas here there is no problem like that. So, this is called the direct method of FM generation. Okay. So, let us try to see now how do you do a FM demodulation. Okay. So, our next target should be FM modulation is almost done. So, we have learned narrowband FM how that can be generated. Then for wider band FM we have seen two methods, one is direct, one is indirect. So, in the indirect method we have to just put frequency multiplier, and we have seen also how to adjust the center frequency as well as the frequency deviation, whereas in direct method it is just choosing a proper VCO parameter. Okay. Sorry, the direct method it is just choosing a proper VCO parameter and it is very easy. Just across the varicap you give your input voltage and you will be getting your corresponding FM modulated output at the output of that VCO. Okay. So, let us now try to discuss about FM demodulation. Again you will see just the mathematics tells us what should be the FM demodulation. Suppose I have a phi FM t, and what it is? It is a cos omega ct plus kf right. This is my phi FM t. I want to demodulate it. The first thing that I will do is, if you carefully see this, if I just differentiate this signal. So, let us try to do this. What do we get? So, simple differentiation you do. So, whenever we differentiate it should have that chain rule. So, differentiation of cos must be giving me sine, and then inside part also has to be differentiated, right. So, inside part if I differentiate, this must be omega ct must give me omega c, because I am differentiating with respect to t, right. And then kf is a constant, differentiation and integration actually cancel each other and this will give me mt, right. So, that is the whole thing that I get after differentiation, and cos must be also differentiated. So, that must give me sine of omega ct plus Kf right. So, what we can see that FM modulated signal, if we just differentiate, what happens, it will generate another sinusoidal, but the whole signal varying part comes into the amplitude. Okay. Now, what we do, whatever the sinusoidal, so it will actually look like this. Suppose ideal differentiator, how does that look? That is generally j 2 pi f, okay, differentiator d dt if you take the corresponding Fourier transform. So, that looks like this. So, ideal differentiator should be something like this, constant means if I put the amplitude part of it. So, that should look like this, it is a linear function of f. Okay. So, if my omega c is somewhere over here and it remains linear over there, means if it is an ideal differentiator. So, I should be expecting something like this from that, that is the output. Okay. And after this, how the signal will look like? So, I had initially a FM modulated signal, so which was having something, some modulation. So, it was varying with respect to the amplitude of it, it is just the frequency deviation. If I just differentiate, what happens, this frequency variation also comes into amplitude whenever there is a higher variation of frequency. So, basically I will have accordingly a higher amplitude, and correspondingly if there is a lower variation I will get a lower amplitude, right. So, this will be, means once I pass it through a differentiator, it will look like this. And inside also same pattern will be coming. Something like this. Okay. This is something which will be happening. So, whatever is happening, what we can see, that message signal is almost in the envelope. So, all I have to now do is a envelope detection, nothing else. As long as I can ensure that envelope detection gives me a signal back, as long as this is not doing a zero crossing. We have already learned that in AM modulation. So, what is the condition that this will not be crossing 0? If this remains always positive, so that means I have to write Kf mt plus omega c must be greater than 0, right. This is something I will have to write. Now, what is the minimum value of this, where it might cross 0, that means the minima of this must also, this is true for all t, that means the minima of this must be also greater than 0. So, minima let us say that is minus, or that is minus mp, let us say. Okay. So, then I can write minus kf into mp, where mp is a positive number, minus of that is the minimum, plus omega c must be greater than 0, greater than or equal to, or omega c must be greater than equal to kf into mp. So, this is the condition I get. What is kf into mp? That is the frequency deviation we have talked about. Okay. So, basically my carrier frequency must be bigger than frequency deviation. This is something which always I will be doing, because if the carrier frequency, because I know from Kurzon's formula that the bandwidth is more than 2 times of this deviation. If my carrier is not even bigger than this particular thing, there will be aliasing, right. We are actually putting at the carrier omega c. Now, the bandwidth is definitely bigger than my del f, twice of del f, right. So, or del omega c. If this is already bigger than my omega c, then what will happen? This will come even beyond 0 and there will be aliasing. So, definitely I will, whenever I do FM, I will make sure my omega c is bigger than that del f at least. It has to be bigger than del f plus b according to Kurzon's formula, right. So, it has to be done. If that is being always done, so this condition will always be there, that is prevalent, we know that this will be happening. If that is the case, I know that the envelope will always remain above 0, it will not have any 0 crossing. So, I will actually, this is guaranteed that I will never have to cross 0. So, if I just detect the envelope, I will get my signal back. So, that makes the FM demodulation pretty simple. All you have to do, you have to pass it through an ideal differentiator followed by a simple envelope detector, the one we have designed for AM demodulation. So, this is what happens, and you know that it is guaranteed as long as you make sure that the FM modulated signal that you generate, that is not creating aliasing, that means omega c is bigger than at least that del omega, you are pretty sure that your envelope will be above always, and if you just track the envelope you will get your message signal back. So, tracking the envelope will give you omega c plus kf into mt. This term will be gone because you are just tracking the envelope, that sinusoidal variation will be gone. So, you will just get a omega c plus a kf into omega mt. Now, this is just a DC term, you block the DC with a capacitor, you will get this part which is the message signal. So, this method of means this differentiator induced method of FM demodulation, that is very simple. All you will have to do is you have to find out an ideal differentiator circuit. Now, we will discuss about that, that is little bit difficult to find out an ideal differentiator. Okay. So, generally what people have done means you cannot actually get an ideal differentiator, that is not possible in circuitry. Every capacitor will put, there will be some spurious resistor in that capacitor, there will be some other effect, and always you will see that it cannot work as an ideal differentiator. So, that is not possible, there is nothing called ideal differentiator. What we will do, we will employ something like this, a CR circuit. This is actually a high pass filter, right. So, how the high pass filter will look like? It will actually look like this. But there is a region, generally high pass filter we are not bothered about this roll off, generally we want to neglect that roll off. In high pass filter we are more concerned about the where the filter response is flat, but this is for the FM demodulation, we are actually bothered more about this roll off. So, we want to see where exactly it remains linear, that is where it almost behaves like an ideal differentiator. So, basically we have to target a particular frequency zone, or we have to design our high pass filter in such a way that in the frequency of interest, which is this omega c and around, that del f plus and del f minus, right. So, that region it remains linear. Okay. So, that is something we will have to find out. So, let us for our ideal this particular filter, let us try to see the what is the transfer function. So, that should be j 2 pi f r c, if you just put it accordingly. So, this is what we get, okay. H f will be just this, okay. Now, this can be approximated as j 2 pi f r c if this 2 pi f r c is much less than 1, because then this term will be neglected. So, there will be only 1. So, I get this. This is almost like a ideal differentiator. So, this will happen if this condition is valid. So, now I can get a condition on my omega c. Okay. So, what I can do, this 2 pi f c let us put as omega c. So, omega c must be much less than 1 by r c. Okay. So, this is the condition I get. If I choose it accordingly, then the omega c will be falling in this region where it looks like ideal differentiator. So, all I will have to do is I have to choose a RC corresponding to my omega c that has been put over there. Accordingly, I put my RC. So, maybe I can fix C and then try to find out what should be my R, and then try to find out a RC value which is much bigger than this omega c. Then I know that around that omega c it remains linear. because this particular transfer function characteristics will be valid, that approximation also will be valid, and it will almost behave like a ideal low pass filter, high pass filter, ideal differentiator, right. And then if I just pass my signal through this, at the output I will get a differentiator or differentiated output at that particular frequency. So, this is all that I will have to do. It is simple enough. All we will have to do is we have to design our RC accordingly and then try to get a particular differentiation circuit. Once this is being done, I know that envelope tracking will be very simple. Whatever we have done at AM, that has to be mimicked over here. Okay. This is one way of demodulating FM. There is another way, okay, that is FM demodulation using PLL. Okay. So, if you remember that for PLL we have also used a VCO, right, that was how we have designed PL. So, for FM modulation we have already used VCO. Now, for demodulation also we will be just using PLL, and PLL also as VCO in it. So, basically FM modulation, demodulation both will have key component as the VCO. So, once you have VCO you can do both modulation, demodulation if we can appreciate this particular circuitry. So, let us try to see how FM demodulation can be done with a PLL. So, this is another application of PLL which is coming out. Earlier we have seen that for carrier tracking probably PLL is very good, and with that target only, because we are talking about phase lock loop which was with the target of carrier locking, carrier phase and frequency locking. We have discussed about that effectively. So, now we will try to see the other application of PLL, which is FM demodulation. So, let us say the PLL generate a means its input this one to which it gets locked, that is a sinusoidal. So, that is something like sin omega Ct plus some theta it, okay, where theta it is the input. So, what we will do, we will actually give this FM signal, FM modulated signal to the PLL input. So, what will happen to this theta it? That must be whatever phase it is getting. So, FM is A cos omega Ct plus the FM modulated part, that kf into At. Okay. So, that means that theta it must have this kf into At plus, because it is cos and PLL input takes sine. So, there should be a pi by 2 phase shift. So, therefore, my theta it should be kf integration minus infinity to t m alpha d alpha plus some pi by 2. Okay. If this becomes theta it, so immediately I can put my FM input should be A sine this omega Ct. So, I can put A sine omega Ct plus this theta I, which is kf integration minus infinity to t m alpha d alpha plus pi by 2, right. That immediately becomes cos. So, it is A cos omega Ct plus this, that is actually FM signal. So, therefore, if I wish to put FM signal to PLL input and if we correspond it, we get my theta it as this one, right. This is fine. Let us say the output phase error that is generated due to the locking, that is theta e. Of course, this should be small enough, we will see that. So, basically, therefore, what is theta output t which is being generated after the VCO, means the PLL output, that should be this input phase minus this theta, right. So, input phase is kf integration minus infinity to t m alpha d alpha plus pi by 2 and minus this theta et, right. So, that is what it will lock to, and it will get this output phase. But what we also know that this theta ot, if we now try to see the error signal that is being generated by PLL. So, that is E0t, that is nothing but the differentiation of this output phase. So, and with a factor 1 by c, which is the factor of PLL, right. So, 1 by c differentiation of theta ot. Now, let us try to differentiate it. So, it should be 1 by c, and if theta OT we have to differentiate. So, this term will be gone. I will have a differentiation of this one and I will have differentiation of this one. So, differentiation of that one is kf, and if I just differentiate, integration differentiation cancels each other. So, I get mt, right, and I will get differentiation of this. Now, that is exactly the error frequency, because phase differentiation is the error frequency. PLL, if it is properly locked, then frequency error must be 0. So, this I can almost say it should be 1 by c kf mt, which is very good, because that is actually the message signal with some constant factor, which I do not bother. So, basically at the error of PLL I get FM demodulated signal if I give at the input of PLL FM modulated signal. That is whatever analysis we have done for PLL, that actually directly comes from, means it directly comes from there. If we just take a PLL circuit, earlier we were not bothered about the error signal of PLL, we are not bothered about that. Now, in this particular demodulation, what we will try to do, we will try to, suppose at that time we were bothered about the VCO generated output. Okay. Now, we are actually looking into the error signal that is being generated after the PLL, after the loop filter probably. So, what we have to do is we will give as input the FM modulated signal. We do not actually tracking, we are not tracking anything. So, we are not worried about the VCO generated output, we are not worried about now we are not worried about that. We will take that from the loop filter, whatever is coming out, we will take that and we could prove mathematically. Again you can see why we are able to use this, because mathematically this is getting proved. So, it is the circuit almost operating the way it is defined, its transfer function and everything operating on the signal, this is what it is giving. So, once you prove that mathematically, you know that with this circuit I can do these things. So, we can see that the error signal is actually becoming the differentiation of that particular thing. Okay. So, differentiation of this output signal, and that happens to be proportional to my message signal. So, that means at the error I am getting my demodulated signal, right. So, what we have so far done is we employed two methods of FM, one was direct method, one was indirect method. In direct method we could use VCO, in direct method we had to do a lot of things, a lot of multiplier part, a lot of nonlinear circuit and all those things. And then for demodulation also we could see there are two methods, one is through differentiation followed by envelope detector, which is simple enough. So, for differentiation you will probably have to employ a linear part of a high pass filter, okay. And the other part is just use PLL for demodulating FM signal. So, these are two things that can be done to demodulate FM signal, okay. So, so far we have analyzed about FM bandwidth and how we can generate or demodulate FM modulated signal and FM demodulated signal, okay. So, this is something we have analyzed, but first of all we need to understand that why we should study FM or why one should employ FM. So, this is something we will now be exploring. So, we will try to see or try to appreciate that FM has some good characteristics. Initially people would have thought probably it is the bandwidth efficient protocol, bandwidth efficient modulation technique, but that is not the case. We have already proven that this is not probably as bandwidth efficient as any of the AM modulated signal, but there are some advantage, and this is something which we will be exploring next. So, the first thing is we have already discussed that there are any modulated signal that you will be transferring that has some effect when it is passed through a channel, right. So, what are those effects? The first effect we have discussed is if the channel is nonlinear, okay. So, that is the first thing which happens. So, we have also seen that if we have AM modulated signal and if there is a nonlinearity, there will be detrimental effect. This is something we have already appreciated and we have seen that, okay. So, what we now wish to see that for FM is there any effect, or is it very very much superior in terms of modulation that any nonlinearity in the channel can be just rejected by FM. Okay, so that is something we wish to see. So, let us try to appreciate that. So, let us say we have an arbitrary nonlinearity. So, y t is some a0 plus a1 x1 t, sorry xt is the input, a2 x square t, some nth order nonlinearity in the channel. Now, what will happen? I will be launching FM signal. So, FM signal, that means my xt should be a cos omega c t plus kf integration minus infinity to t m alpha d alpha. So, whatever discussion we are doing, that is equally valid for FM as well as PM, right. So, both are equivalent, that is something we have proven. Instead of integration, you will be putting just empty over here. Okay. So, if I just put this xt, what will be my yt? This is something we have just done for our direct modulation, right. So, what will happen if I just put it over here? I will be just seeing something like C0 plus C1 into cos, of course this A can be taken inside C. So, do not worry about that. So, it should be cos omega c t plus kf minus infinity to t m alpha d alpha plus cos C2 cos 2 omega c t plus kf 2 kf and so on up to nth term. But what has happened now, this FM modulated thing, after it passes through this particular channel, will probably get all these extra higher terms, and my receiver, what generally that will have at the front end of receiver, we have already talked about that it wants to neglect the effect of noise. So, it will have a band pass filter, where that band pass filter will be centered at omega c, and the band will be just the FM band. So, if I just pass it through that band pass filter, these things all will be neglected. So, all those higher frequency term where this is getting contaminated because the frequency deviation is getting twice, thrice and all those things, they will be all cancelled out. What will happen? I will only have this particular thing. So, even if I have channel nonlinearity, I do not bother about it, because FM automatically due to that band pass filter will cancel out that effect of nonlinearity, and it will get pure FM modulated signal even after passing through a nonlinear channel. So, that is a very big advantage which FM has, or FM has that edge over amplitude modulated signal, because in amplitude modulated signal, if you multiply it, that m square t term will be coming out, okay, because it is in the amplitude. So, that multiplication will create a multiplication in the signal also, and then that will create problem for you, whereas that is not happening over here. Okay. So, that is a big advantage which we will have whenever we have a channel which is slightly nonlinear. So, in that channel, if you just put FM, that is more protected compared to your any form of AM modulated signal. Okay. So, this is the first thing where we could get some advantage of FM. We will see if there are interference. See, whatever I have told, that is actually creating a source of interference also. So, if the channel is nonlinear and I have here probably at omega c my FM signal, but at 2 omega c there might be some others FM signal, where due to these things in the channel they will be all created. So, this will create interference to them. However small that nonlinearity is, this A2, A3 coefficients are small, they might be smaller, but they will still create some effect at those frequencies. So, those are treated as interference. So, what we will see in the next class, that in presence of interference, how FM survives. Okay. So, that is something we will try to appreciate in the next class, and then at the end we will also try to do noise analysis, and we will be able to prove that in any time in any channel, FM is much better in terms of noise cancellation compared to any of its AM counterpart. Okay. So, that is something we will be proving, and with that we will probably end our discussion of FM. Okay. Thank you.